All right, first video, you guys. Hopefully you found this okay. Today we're going to talk about, this is entitled LMP, but it's really because we're going to talk about the law of multiple proportions. There's a page in chapter 2 where it talks about a variety of laws, like the law of conservation of mass and the law of constant composition and the law of multiple proportions. And, just sort of so that you know, the law of constant composition is just referring to a single compound. I'm not going to really belabor this one at all, but the law of constant composition is referring to within a single compound, if no matter when or where you find it, it's always going to have the same kind of ratio of one element to another. So that's one law, but the one we're going to spend more time on actually deals with more than one compound that contains the same element, and that's the law of multiple proportions. So I'm going to go through an example of this with you today so that you can, proportions, hopefully spell that right, so that we can understand what this means. Now I'm going to write down basically the definition of the law of multiple proportion, which is this: the masses of one element that combine with a fixed mass of a second element are in a ratio of small whole numbers. And I'm going to bring that up because really this definition makes it sort of difficult to kind of understand what that means. So what I want to do then is I want to go through a numerical example with you in order to kind of explain this idea. So we're going to look at an example that deals with a copper oxide. And you can take a copper oxide, and it's possible. Now there are two types of copper oxide that exist. There's copper 2 oxide and there's copper 1 oxide, and both of those could be decomposed into its elements, copper and oxygen, and then of course we should balance this equation. Or this one could be decomposed into its elements, which of course are also copper and oxygen, and then we should balance it. So both of these two things could happen. And so that's what the law of multiple proportions is about. It's about looking at two compounds or more compounds that have the same elements in them, but they are different compounds. So let's say that we did a lab. And in that lab, we had a sample of, we'll just call this copper oxide. We'll call that we have copper oxide A. And let's say that we also have copper oxide B. And if we were to do a lab where, let's say it was heated up and it decomposed, and in both cases, no matter what copper oxide it is, our products would be copper in the end and oxygen in the end. But let's say we took some data. So if you had copper oxide A, let's say that we started with a 10-gram sample. And let's say it was heated up and it decomposed. And in the end, what you had in your flask, because you started with this sample, the oxygen left. And so what remained in your sample was just copper. So in the end, let's say you took a mass of the copper that remained and you had 7.988 grams of copper that remained. Well, with that, we certainly can use this information here in order to figure out how much oxygen left. I mean, that's just a simple, oh, no, use a highlighter there. That's just a simple subtraction. And so you could figure out, oh, there's 2.012 grams of oxygen that must have left the container. Now, just as a side note here, it is possible, based on these pieces of information, to figure out what the empirical formula is. Because if I know there's 7.988 grams of copper and 2.012 grams of oxygen, I could convert that into moles of copper. I could convert that into moles of oxygen and then divide by the smaller and find out what the ratio is and figure out what the formula is. That's not my attempt here right now. I'm not trying to show that, but you know, your book will kind of show you some of that. You might want to look up empirical formula. It's certainly a wise idea to be able to do that. And you'll have to do some of that in the lab. But here's what that, well actually, sorry, I'm getting ahead of myself. Let's say we did the same exact experiment with copper oxide B. And in copper oxide B, we took a 10-gram sample of it and we heated it up. And same thing as what we saw here, you know, the oxygen would leave and the copper would be left behind. And so let's say that we took a mass of the copper that remained, and it was 8.819 grams of copper that remained. And so certainly we could figure out how much oxygen was left. We could just subtract that, and we find that it's 1.119 grams of oxygen. So notice we started with the same amount of sample. This is probably not the same compound, which is why finding that empirical formula would be a very reasonable thing to do with some of this data. Find out, you know, again, you could convert that into moles, find out how many moles of copper there was, and find out how many moles of oxygen that was, and see what the ratio was between moles of copper and moles of oxygen. You know, looking back at our original problem, you know, in this one we would expect to see it be 1 mole of copper to 1 mole of oxygen, and here we would expect it to be 2 moles of copper for every 1 mole of oxygen. So we could figure out the empirical formula that way. But let's go back to the law of multiple proportions. The law of multiple proportions says the masses of one element that combine with a fixed mass of a second element. Well, I've got, in copper oxide A, I've got 7.988 grams of copper, and copper oxide B, I've got 8.819, and I've got differing amounts of oxygen. So I need to try to get that. I'm going to try to find a ratio. So for copper oxide A, I'm going to do a ratio of copper to oxygen. So 7.988 grams of copper to 2.012 grams of oxygen. And if you plug that into your calculator, you get 3.970 grams of copper for every 1 gram of oxygen. Kind of tells me how much copper I get for a gram of oxygen. Well, I'm going to do the same thing with copper oxide B. I'm going to take 8.8819 grams of copper and 1.119 grams of oxygen. I'm going to divide that out so I can find out how many grams of copper there are per 1 gram of oxygen. So I divide that out on my calculator. I get 7.937 grams. Oh, that's not. 7.937 grams of copper per gram of oxygen. All right, let's go back to the definition. The masses of one element that combine with a fixed mass of a second element. Well, that's what we just did. Here's our fixed mass of a second element. We found out how much copper combined with a gram of oxygen for this one, and then we found out how much copper combines with a gram of oxygen for this one. So we've just figured out how much combines with a fixed mass of oxygen. That fixed mass of oxygen is 1 gram. The law says those masses are in a ratio of small whole numbers. So here's an interesting thing. That means that the ratio of this to this is a small whole number. So let's see. If I were to take 7.937 grams of copper for 1 gram of oxygen and try to put it in a ratio, I'm going to put the bigger one on top because I just like bigger numbers instead of fractions, put it over the other one, 3.970 grams of copper per 1 gram of oxygen, I get 2. I realize I don't have all my significant figures there, but this is a ratio of, it turns into a whole number. It's in a ratio of small whole numbers. That's what it's referring to. So what does that tell you? This one, remember, was from copper oxide B. and this was from copper oxide A. What that tells you is that there's 2 times as much copper in B as there is in A. That's what the law of multiple proportions is. They didn't know about moles at the time. So everything, notice, all of my calculations are done in masses, not moles. Because they didn't know about moles when this law was created. So it's really a way for them to figure out that, hey, there is a relationship when they have the same elements but different compounds. Now you can do the empirical formula and find out that this is really copper oxide B is C2O and copper oxide A is CuO. And look, there is twice as much copper in B as there is in A. And I would encourage you to do the numbers and see if you could come up with that. Now let's kind of just transition. We're going to be making a compound in our lab on Monday. Now you have a copy of the lab, but here's the basic idea. You're not going to be making a copper oxide, you're going to make a copper iodide. So this is a copper iodide lab. But copper could be copper 1 or copper 2, so we don't know what iodide of copper you're going to make. But what you're going to do is you're going to get a piece of kind of copper foil. And what's going to happen is you're going to actually bend that piece of copper foil into sort of like a V shape. That's back behind it. And you're going to sprinkle some solid iodine onto this piece of copper. And then you're going to heat it up. Well, what happens when you heat this up is a reaction is going to start to occur. And what will form is you'll get actually a layer of a copper iodide. Now there's going to be some excess iodine, and that's going to kind of leave sublime as iodine gas, a nice purple vapor. We're going to do this in the fume hood. It's actually really cool to watch. But you're going to produce a copper iodide. Well, your job, you need to figure out what copper iodide is it. That's going to use a little bit of your empirical formula knowledge. And then we're going to give you some information to help you to prove the law of multiple proportions. So that's what's creeping up on Monday. Don't forget your shoes. Don't forget your lab notebook. Those are things that you need to bring on Monday. And I gave you a copy of the lab, so you certainly want to read that over as well. All right, we'll see you guys Monday.